on it.
Oh,
I thought I did, but
yeah, that's okay. I'll figure it out.
I submitted it again with my name on it, so if you see two that are like one right
Maybe
after
right
the
next
other,
to each other.
it's
Okay.
me. Sorry.
All right. So we are almost done. This is the second to the last week of class, then final exams. We're looking at optimization problems.
On Monday or Wednesday? Tuesday.
I have no idea when the final is. Somebody asked yesterday and I forgot to look. I think I might have posted it to the syllabus. Where's the syllabus? Is it
It's a
in
week
here
after.
somewhere? It is.
It's a week after Thursday or Friday?
Oh, not next week, the week after.
It's the first week of December.
Thursday.
Thursday.
Oh, wait. That's because it's an online class too. All right, let's see what the official time is. Let's see. Yeah, for online students, it's no later than Thursday because my grades are due Friday morning. Let's see. Academic calendars, final exams, and we meet
The second one?
Tuesday, Wednesday, Thursday, Friday at
11.
Ah, no, Thursday at
Thursday.
10. Damn, that sucks.
So it is on Thursday.
It is on Thursday. Yes, if you want to take it sooner, let me know. I'd be glad to give it to you Thursday. Otherwise, it's going to be a challenging day to get all those graded in one
Isn't
day.
that what it says on
But we can take it, and you'll let us take it any time during the week?
You can take it anytime during the week. Yeah, our official time is 10 o'clock on Thursday the 6th for the final.
Me too.
Okay, so let's do it. We established the other day that we needed a volume for a can that was 1,000 cubic centimeters. Formula for volume is on the can pi r squared times h. Circular bottom and then root the height. The surface area, let's just call it S or A for area, say, is going to be a circle at the top and a circle at the bottom, so that's 2 pi r squareds. And then when we unroll the label, we get a length times a width there. The length ends up being the circumference, 2 pi r, times the height. So that's the surface area of a can. Roughly, but we have too many variables. We established right at the end of class yesterday that we can solve this for h, for example. We could also solve for r, but I think solving for h is easier. And so then we get h is equal to 1,000 divided by pi r squared. And what we'll do is we'll substitute that in for h right there. Then the area will be just a function of the radius, given that we have this fixed volume. If we didn't have a fixed volume, then we have a multidimensional problem, and we're not going to do that. So substituting that in, 2 pi r squared plus 2 pi r times 1,000 over pi r squared. Things clean up a little bit. The pi's divide out. R divides with one of those r's in the bottom. Bless you.
Thank you.
So then I get an area function in terms of r of 2 pi r squared plus 2 times 1,000 over r. And for the sake of doing a derivative, I think we'd be better off writing that as r to the negative 1. All right, so take the derivative of that sucker. What is dA dx, Rob? Well, let's see. Derivative of r squared is 2r times 2 pi. So we'll get 4 pi r. And then we want to add on at 2,000 times the derivative of r to the negative 1, which would be negative 1 times r to the negative 2. And we need to clean this up. So let's see. 4 pi r minus 2,000 over r squared. And considering critical numbers. So right away I can look at this and see that, well, if r is 0, it's undefined, but if the radius is 0, I've got no can. So that's not my domain of consideration. So then we just need to set it equal to 0 and find critical values that way. So let's see, solving this, I guess I would add the 2,000 over r squared to the other side. So we'll get 4 pi r equals 2,000 over r squared. What do you think? Multiply both sides by r squared. The r's on one side. And then divide by the 4 pi. Almost done. Taking the cube root, I get r is equal to the cube root. And I guess that simplifies a little bit. 4 gives me 2,000, what, 500 times? 500 over pi. And let's see what that is approximately. Anybody get that on their calculator? Cube root 500 over pi. Let's go to 3 decimal places.
You said 500 over pi?
500 over pi, cube root.
Oh, 5.4192. We'll add 3 if you round.
0.41, let's call it 9. We'll go to 3 decimal places. Cool. What's h going to be? Well, we know that h is, what was it, 1,000 divided by pi r squared. So what happens if you plug r, that value r we found, into that? What do you get? To 3 decimal places.
I got 10.510.
510 to 3 decimal places? Huh, interesting. That looks close to twice the radius, isn't it? Kind of curious. Let's double check that. So if we plug in the exact value here, then we're going to get the cube root of 500 over pi here. And then we have to square it. So let's see, that would be, what's that?
Actually, I put in a 3 instead of
Oh, you typed it in wrong?
10.838.
Oh, that looks,
839.
that looks closer to double.
Yeah.
839?
Yeah.
Okay.
It's 8385.
8385, okay. So I just want to double check here with the exact answer. So that would be 1,000 over, and then I have pi, and then that would be the power 2/3. So I'd have 500 to the power 2/3 divided by pi to the power 2/3. So bringing together like factors, 1,000 is really 2 times 500. And then I can consider the other 500 to be 500 to the negative 2/3. And then down below, I'm going to leave the pi's down there for now. That would be pi to the power 1 minus 2/3. So what does that give me? That gives me 2 times, let's see, 500 to the 1 times 500 to the 2/3 basically gives me 500 to the 1 minus 2/3, which is 500 to the
1/3?
1/3, yeah, so I'm going to get 500 to the 1/3, and then pi to the 1/3, and 1/3 is the same as what? Cube root. So what I have here is twice the cube root of 500 over pi. So it is twice the radius. Whoa, the optimal size can, the diameter is twice the radius. No, so the height is twice the radius. But wait, how's the diameter related to the radius?
It's twice the radius.
It's twice the radius. So the height is twice the radius. The diameter is twice the radius. So what is the cross section of this can vertically?
A square.
It's a square. Oh my gosh. Yes. The can we need, when you look straight on, is going to look like a perfect square because the diameter and the height are going to be the same. They're going to both measure 2 times the cube root of 500 over pi centimeters, which is going to be about 10.8-ish. Is that what we calculated? And that's going to be the same thing for the height of the can, 2 times that cube root. So we should probably calculate the surface area also. What is that minimum surface area? So that means we would just go and plug back in. And we can plug into either version. Usually you go back to the original plug-in. The original area formula is 2 pi r squared plus 2 pi r h. We would plug r and h in there. So I'm going to check this in a couple of different ways after we calculate that. So let me get my calculator out. Desmos. So what do I want here? I want our modified area. So the area according to x, I can't use r, is equal to 2 pi x squared plus, what did we simplify that down to? 2,000 divided by x divided by r. That's our simplified version. Two pi x squared 2,000 over x. Yep. All right. And then we calculated that the minimum, the optimal radius was equal to, parentheses, 500 over pi. Ooh, is it going to let me use r? Looks like it might want r to be a polar thing. Raised to the power 1/3. Did I do that right? Oh yeah, it's doing polar. Okay, that's bad. We'll call that a 5.419. Okay, and for the surface area, I want to know what the area is when I plug in that little value. I get 553.58-ish. Anyone else get that? Skylar gave me a thumbs up. Cool. So 553.581, if I plug in exact values, let's add that to our information here. And where's the right one?
If you put it on the.
Thank you. So How many again was it? 553.
0.58.
58. Units of that would be what?
Centimeters squared.
Centimeters squared, right? We're doing area, yeah. So square centimeters or centimeters squared. Yeah, so that should be the smallest we can get the volume. Let's look at the graph of our modified single variable function to see if it really does. Shouldn't it have a minimum there, right? Let's verify that this is a minimum. So I got to adjust my viewing screen here. X, I can let go from 0. Let's go up to 10. That's fine. Y, I need to go up past 500. So maybe I'll go up to like 800, give myself a little breathing room. Ooh, check it out. It's dropping down quite nicely there. And then if I choose the curve, Desmos will try to approximate that minimum, 5.419, and then 553.581 square centimeters would be that minimum area. So the goal here was given 1,000 cubic centimeters or 1 liter of volume, what size can optimizes the area of the can. So 2 answers to this question. How do we define the size of the can? Well, we need to give the radius and the height, correct? So that's part of our answer. And then the other part of the answer is what is that minimum area, right? And that's the 553.58. Okay, so in this case, we're going to have 3 different answers for this. The dimensions of the can, and here I show the diameter and the height. And then that optimal surface area, given that we had a volume of 1 liter, which is 1,000 cubic centimeters. Pretty cool, huh? All right, let's try another one. So, let's see, what else did I want to do here? We did one, no, we didn't do one like that. We could do that one next, that's similar. Similar. Ooh, that's a good one. All right, I'm gonna pick a homework problem. Has anyone played around with the homework and gotten stuck on anything yet? Not yet? Okay. Let's see. All right, how about, so this box with the open top is kind of the reverse of the problem we had the other day. Yesterday we had a fixed like surface area and we wanted to get a maximum volume. Here we're given the volume and we want to minimize the surface area of the box, which is like the can problem we just did. This is the problem we did in class yesterday. Okay, number 3 is a wee bit different. A rectangle is inscribed with its base on the x-axis and its upper corners are on the parabola. What are the dimensions of such a rectangle with the greatest possible area? All right, let's take a look. So y equals 8 minus x squared. Let's see if I can draw that. So y equals 8 minus x squared. This is going to have intercepts at x equals plus or minus the square root of 8. Square root of 8 is what?
Just under 3.
2 point something? Somebody give me a little, like 1 decimal place on that?
2.8.
2.8? Okay. So that's about plus or minus 2.8, and y-intercept is 8. So graph of this thing. 1, 2, 3, 4, 5, 6, 7, 8. And then 1, 2, 3, 1, 2, negative 3. So we've got, oops, not exactly there. Well, point bigger, there-ish, there-ish, and there-ish. So here is my parabola, something like that. And I have a rectangle somewhere in here, like that. And I want to maximize the area. So we're going to come up with an area function for this and figure out how to maximize it. Well, area of a rectangle is base times height. The base of this thing is, well, given this is some x value right there in my domain, the base would then be 2x, right? Because we can go x this way and x that way. So I've got 2x for the base. And the height is, I basically plug into that function, and I see what it tells me the height is. Right? So the height's the y value of that point, and the y value is given by that equation. So the height is 8 minus x squared. That make sense?
Mm-hmm.
So the hard part of these problems is the setup. Once it's set up, then we just fly through the calculus. So I'd like to multiply those together. So my area function in terms of x is going to be 16x minus 2x cubed. And we're ready to take the derivative. Switch colors. So derivative of a with respect to x is going to be 16 minus 6x squared.
Mm-hmm.
And we need to set that equal to 0 and solve. So then I'm going to get 16 equals 6x squared. Divide by 6. And take the square root. So I'm going to need a new page for that. So what's that going to be? The square root of 8/3. Now technically it's plus or minus the square root of 8/3. But I'm just considering x to be the positive version of the number, so I don't really need the minus. Anybody with a calculator, that is approximately what?
1.63.
1.63-ish. So let's just take a look here. That would be 1.6-ish, right about here. So roughly that rectangle right there should give me the most area. Interesting. What's special about that rectangle? Kind of curious what the height of it is, right? Because before, when we looked at the can, radius and width, an interesting feature popped out. It had a square cross-section. Does something interesting happen here? And is this the right answer? Oops, got it in the wrong spot. So y would be equal to 8 minus that number squared, right?
Yeah.
And so if we square a square root, they cancel. So that's going to give me 8 minus 8/3. So let's see, 8/3. I have to multiply this by 3, top and bottom. So 24 minus 8 is 16 on a good day. So y is 16/3. Interesting. What pops out as interesting about that?
Yeah, that is double.
It's double the square of the x value. Not quite, not double the x value. Interesting. What is, let's see, approximately 3 goes into 16 how many times? 5 times?
Yeah.
With 1 left over.
Mm-hmm.
5.33-ish versus 1.63. Do they have any interesting properties? I don't know. Let's see. If I take the SQRT of 8/3 and divide by 16/3, I get 0.3-ish. It's not that exciting. The other way. 3.26-ish. I don't recognize that as an important number. I don't see any significance in the ratio of the height to the width, but I think we found the right answer. How do we know if we found the right answer? We need to check some way. So a couple things to consider. The dimensions. So for our answer here for the optimization, we should give the dimensions of the rectangle. Okay. So we found that x, let's pick a different color, here we go. X is going to be exactly that square root of 8/3. And I don't see any point in cleaning, like rationalizing the denominator is not all that important here. So the base of our rectangle will be twice that, so twice the square root of 8/3. And the height of the rectangle is going to be 16/3. And so the other important number is our optimal area, which is just going to be base times height, which cleans up a little bit, I guess. So it's going to be that twice the square root times 16/3. Yeah, and I guess if we rationalize the denominator, that cleans up a little bit, but nothing dramatic. Anybody have an approximation on that number? Supposed to be weight equals, and
Ooh, hold on, that's not the right one.
Uh, 17.42 could be around.
and that's squared, whatever the units are. I don't think we were given units there. All right, so next, is any of this correct? I don't know. How do we figure that out? Well, we're going to do two things. We're going to graph the function and see if what we did looks reasonable. Now, graphing the function isn't this picture right here. It's this one right here. Okay. The other question is, do we have the right area function? Double check our logic. Area is base times height for a rectangle, right? Yep. The base is going to be the distance from this x value to that x value, which seems pretty reasonable. That's going to be 2x. With me? Okay. And the height is whatever y says. Okay. So I think that's reasonable. Let's double check to see if this indeed has a max. So looking at the graph of it, let's bring up a new Desmos tab. We have, let's see, 16x minus 2x cubed. Does that sound right?
Mm-hmm.
And Desmos is kind enough to say, hey, 1.633-ish should be the x value you need, and 17.419 or 17.42 should be about the area that you need. Because this is the area function, right? Not a picture of the area. All right, I think we did good. Questions? All right, do another. What else looks exciting in the homework? Let's see. The problems at the end usually tend to be exciting. Oh my. That looks exciting. Fence, not bad. Point on the curve. Oh, that's a good one. Norman window. If you don't know what a Norman window is, look it up. You'll get a nice picture of it. All right. So I say we either do 9 or 11. All right, let's do 11. Okay, so number 11, let's zoom in on that a touch. All right, Centerville is the headquarters of Greedy Cablevision Incorporated. The cable company is about to expand service to 2 nearby towns. There needs to be a cable connecting Centerville to both towns. The idea to save on cost of cable is arranging the cable in a Y-shaped configuration. Centerville is located at 12.0 on the XY plane. Springfield is at 0.6 and Shelby is at 0.6. The cable runs from Centerville to some point x0 on the x-axis, where it splits into 2 branches going to Springfield and Shelby. Find the location x0 that will minimize the amount of cable between the three towns. Okay, attempt to draw that. Get out a piece of graph paper. Let's see, I'll rough it out on paper. Okay, so. All right, so let's see. Hopefully we have similar sketches. Uh-oh. Well, good thing my other pen works today. So I need x, y, and let's see, that's 6, that's -6, 6, and 12. So right here is where center field is. And then up here is that S Springfield maybe, and Shelby or something like that is the other one. Okay, and then I'm supposed to identify a point x0, so maybe I'm going to pick this x value for now, whatever it happens to be. So my cable needs to go out to there, and then it needs to make a Y shape out to the other two. So that's my cable distribution. So now I just need the length of each of those cables to try and minimize it. Well, Pythagorean Theorem is going to be helpful with these two branches. So according to the Pythagorean Theorem, I need to know a right triangle. And for Springfield, it measures x by 6 for the legs. And yeah, and this one's x by 6 also. Yeah, so I have 2 of those, which isn't too bad. So Pythagorean Theorem says this will be the square root of 6 squared plus x squared. And same thing down here. This one's going to be the square root of 6 squared plus x squared. And then this leg of the journey right there is just 12 minus whatever x is, that remaining distance. So altogether, the cable length, so I guess I'm going to call it L for length, is going to be 2 of those square roots plus that 12 minus x section. So I think we have a reasonable setup. Do you all agree? Mm-hmm. All right, so now it's a matter of differentiating that with respect to x. And in this case, we want the minimum length. So we're hoping that this thing will be concave up in the section we're looking at. So x has to be, it seems reasonable that it's somewhere between 0 and 12, that it's unlikely to be a negative number.
It can't be 12 though, can it? Because it's supposed to be a distance away from.
It's, yeah, so it should be x should be less than 12, but probably greater than 0. So that seems like a reasonable domain. Let's see, according to this square root here, we'll worry about that later. Let's take a drink. All right, switching colors, we want dl dx. So take the derivative of the square root any way you know how. You could use the 1/2 power, for example. Or you can remember what the derivative of the square root is. Yeah, so it's 1 over twice the square root. But that's not just an x inside the square root, so I also need the derivative of the inside,
Which is 2x.
which is just 2x, so that's going to give me a 2x on the top here. So that's one version of the derivative of the square root of 36 plus x squared. And don't forget the times 2 there. What's that? Yeah, things will clean up. I'll worry about that in just a minute. And then over here, derivative of 12 is 0, and the derivative of negative x is -1. So I'm going to have a -1 there. This cleans up just a little bit. So we get 2x over the square root and then -1. And things to consider here, any number that makes the denominator 0 is going to be a problem. And let's see, 36 plus x squared, is that ever 0? It's never 0. Yeah. So we're good. So there's no undefined values, which are good. And often in optimization problems, the undefined critical values, they don't usually help, but sometimes. All right, so we just have to set it equal to 0 and solve. Let's do it. New page. So I have 2x over, let's pick a different color, please. Blue. The square root of 36 plus x squared, excuse me, -1 equals 0. So adding 1 to the other side. Oops. Okay, operations, Gary. And then we can multiply that square root over. Square both sides. Yeah, so subtracting an x over to the left, we'll have 3x squared is 36. Dividing by 3, x squared on a good day should be 12. And so it looks like we want x to be the square root of 12, which is 3 point something. Anybody know what 3 point, how about to 1 decimal place?
3.4 or 3.5 will be round.
3.5 to 1 decimal place?
Yeah.
Okay. So I just want to redraw the picture to kind of envision that, see if there's any geometric significance. I always find that exciting. Sometimes the geometric significance is relevant. So let's see, if we scale, let's go by 3 this time, 3, 6, 3, 6, 9, 12. Come on, there you go. So we got about 3.5 for x, so right about here-ish. So this is our cable distribution. I don't know. Let's see, 12 minus 3.5 is going to be what, 8.5? Is that right? So this length right here is 8.5. And the other ones, let's see, the other ones were the square root of 36 plus x squared. And x was square root of 12. So that's going to be 36 plus 12 is square root of 48. Oops, order, I think. 48 is what, 16 times 3? So that would be 4 square roots of 3, I believe, which is approximately 5 point.
I got a
Something.
6.9.
I got 6.9.
6.9, okay. A square root of 3, right? I just need square root of 2. 6.9-ish for each of those. Well, geometric significance isn't jumping out at me. It might be there. Let's see. Double check. How can we double check? Well, a couple things. We have a function which we believe is how to calculate the length depending on where we decide to put that terminal or that what do you call it? I guess we can call it a terminal, where we branch out. And Pythagorean Theorem, difference, I'm pretty sure the geometry and logic here is okay. So the next thing we should do is double check graphically that this is concave up in the region we're looking at. We could also use the second derivative to determine that. That would be another option.
I think the homework makes you do that.
We're asked for that?
Yeah.
Okay, oh yeah, let's see what the homework asks. Okay. So to solve this problem, we need to optimize the following function of x. Okay, so our function of x is, let's see, twice the SQRT, right? Of 36 plus x squared. And then we had to add 12 minus x to that. So that's our function. Critical number occurred at the square root of 12. And it says I can't enter a mathematical expression. Verify that f of x has a minimum at this critical number by computing the second derivative and find that its critical number is blank. Okay, so we do need to do the second derivative. A positive number, all right. Let's see, double check. Has a minimum, we compute the second derivative and find that the value at this critical number. Okay, so it wants us to plug in the critical number into that to make sure it's positive. Okay, so we need a second derivative. So first derivative is that right there. So now we need the derivative of 2x over the square root of 36 plus x squared minus 1. And we can get away with not using the quotient rule if we wish. Doesn't matter which one we use.
Rule's easier.
Yeah, product rule is probably easier. So we could rewrite that and call it 2x. Yeah, it'd be easier to use the product rule times parentheses 36 plus x squared, and that would be to the negative 1/2, and then we have the minus 1 adding along. So we use the product rule in the first part, and the derivative of the minus 1 is just going to be 0. So the product rule says take the derivative of the first function, 2x, so that would be a 2, and leave the other function alone. And then add on to that the first function, right, times the derivative of the second. So we're going to have a negative 1/2 come down. The 36 plus x squared, 36 plus x squared stays the way it is for now. We drop that power by 1 and then multiply by the derivative of the inside.
2x.
And then there's going to be a minus 0, which we don't really care about. Doesn't hurt anything. We could spend some time cleaning this up, but I don't think we should really worry about that. I'm just going to clean it up a tiny bit. So we're going to have 2 times 36 plus x squared to the negative 1/2 minus 2 times 1/2 cancels, but we do have that other 2x times 2, so we'll have a 2x squared parentheses 36 plus x squared to the negative 3/2, and we want to plug into that the square root of 12. So whip out your calculators. Let's see if we can get an answer. Calculator, all right.
And what f of 12 is?
So this would be f double prime. So we want to apply the square root, plug the square root of 12 into that.
Point 02165.
0.02165.
Yeah.
What number? Yep. A point 0.02?
Uh-huh.
I got
Oh,
point 0.2.
0.21, sorry.
Oh, I got 0.21.
0.2165. Okay. So what we really care about is a positive number.
Yes.
So back here, the value when we plug that in is positive. I'm not going to enter a mathematical expression, although I could. I'm just going to do a few decimal places. So 0.2165, that should be good enough. And again, your number will probably be different. Like the first time I looked at this, mine had a 9 here. Oop, I typed something wrong. I put a 4 in there by mistake. Is that better? 2165, yep. And then the minimum length of the cable is, did we calculate that? We did. What is it? 22.3-ish. Is that going to be enough accuracy? Let's see. Oh, I just roughed it out there. We'll see. It's probably not going to be accurate enough. Submit. And it didn't like that last one. So it wants a little more detail there. So let's see. What was that? That was the square root of 48 was one of those sections. So twice the square root of 48 plus 8.5. So I can just enter that in. Twice the SQRT of 48 plus 8.5. Is that what I said? Submit. No, it doesn't like that either. Come on, what? Okay.
You put minus plus 12 minus.
Well, we approximated the 8.5 too.
Yeah.
Oh, that's approximate too. Oh, maybe that's the problem. It's supposed to be the square root of 12. Okay, so I'm gonna have to go, all right.
12 minus.
Yeah, just do 12 minus the SQRT of 12. And you better be happy with this one. Oh, did I double check any other way? Did we look at the graph of the function yet? No, let's double check that before I use my last chance, because then it's going to give me different numbers. Okay, so let's get here. So we have twice the SQRT of 36 plus x squared. Outside that is plus 12 minus x. And this is supposed to be concave down because I'm minimizing. And so let's zoom. There it is. 22.39. Is that in the ballpark?
Yeah, that's what I got.
Okay. And that's this value right there? Okay, here we go. I'm submitting. Oh, we got it right. Yay. All right. So given that there's going to be a test on this eventually, it's really a good idea to find ways to check before you hit submit, especially before you hit submit the third time. But on the test, remember, you only get one submit on the test because it's on paper. So again, think about ways you can double check. And in problems like this, it's double checking the setup and it's double checking the values we got graphically is what you want to do. All right, out of time for fun with math. Have a wonderful, safe Thanksgiving. We have, what, 2 more sections to cover, I think? Or 3?
Yeah, I saw 3 on the.
There's 3. Let's zoom out here.
We know, we had that 4.9.
I think so, yeah.
Calendar.
Yeah, so.
No, we ended up
Let's see,
with 10.
4. Okay, we have 3 more sections. Yeah, 4, 8, 9, and 10.
And the final is cumulative, right?
Final is cumulative, yes. And so I will, by the end of this weekend, I will have posted a sample final review thing.
At the end of the weekend?
I'll try by Friday.
But it gives you
I'll
a whole
try.
week
Here's my
to
favorite
work
part.
on.
Well, when I told you guys
And then
before,
some.
when I was a college student, I liked the 2 weeks to prepare for finals.
Well, for finals
Margaret
on
Mayer.
Thursday, and you have it posted by Sunday night.